Good morning, everyone. Can everyone confirm if I hearing me clearly? Is everyone hearing me clearly? Okay. Oh, thank you so much. Thank you for confirming that. I want to welcome you to my lecture today, and I want to first appreciate those who actually check on me by sending messages to me. So I think I'm fine now. Okay, like I said, the situation is now under control, and of course, uh, I'm fine now. So I'm gonna say thank you to everyone who actually checked by. Okay, so today, want to walk you through another exciting topic in statistics, and of course, the focus today is going to be on Poisson and negative binomial distribution. Okay, I want to remind you, before now, we actually started, discrete probability distribution. And of course, the discrete probability distribution, of course, I've walked you through what I call discrete uniform. We've already done Bernoulli distribution. We've done binomial distribution. And of course, the last time we met, we actually did, geometric distribution. Okay. And today we basically are going to focus on Poisson and negative binomial distribution. But you know what? I think I need to have a recap on what we've done before. Okay, I told you the other time when we're dealing with the discrete probability distribution, specifically Bernoulli distribution. You know what? Bernoulli distribution is actually used to model, variable that have two possible outcome. And you know what? The sample size have to be equal to one. It means the numbers of trial has to be one. Okay. And of course, we must have two dichotomous outcome as far as Bernoulli is concerned. Well, let me tell you now, when the sample size is now increased. Okay, if the sample size is no longer one, if the sample size is more than one, and there are two possible outcome. Of course, we're basically going to have binomial distribution. Of course, from there I moved to geometric distribution, and I told you in geometric distribution we basically we want to figure out how many times are we actually going to fail before we record the first success. And of course, the other time, I actually show you, I walk you through the probability mass function of, geometric distribution. And of course, today, we're basically going to visit another two discrete probability distribution. And of course, one is Poisson distribution and the other one is negative binomial distribution. Okay, so all of them actually fall under discrete probability distribution. Of course, in the outline today, I'm going to walk you through this, and of course, you're going to learn how Poisson normal, Poisson approximation, to the distribution is actually being done, then Poisson process, then to the negative binomial, and of course the concept of convolution we're also going to be discussed. So let's get started. Now let me tell you now, in statistical analysis, in statistical theory, okay, if a random variable X actually follow Poisson distribution, okay, I'm going to show you now. So this is the mathematical architecture of that, if you take a look at that now, you're basically gonna see S start from 0 to infinity. So the support of X right here, we got an infinite. Take a look at that. And you know what? The parameter of interest here is actually mu. This guy here, okay. And you know what? Um, if I want to write Poisson distribution in a short form, this is how to write a POI, you know, in parentheses mu. So at times, if I write something like this, okay, I'm actually talking about Poisson distribution with the parallel mu. And of course, if you want to specify the probability mass function associated with that, of course, it is this guy here. So take a look at that. That's a Poisson distribution. Okay, now the question now, since I've actually uh, displayed, the statistical architecture of Poisson distribution now, okay, just like every other probability distribution, we expect that when we sum that over the range of the support of X, it should give us 1. You remember the other time, if f of S is a discrete probability distribution, when I sum that over the range of the state space of S, it should give me 1. Okay, so what I'm trying to do here now is to be able to tell you, the summation of that from 0 to infinity, okay, of course, is actually going to give you that. So take a look at that. Now, when you take a look at this now, so which is actually equal to 1, there's a way you can show that, okay? There's a way we can actually show that, okay? Now, this is a way to show that from the Maclaurin series. I want to tell you this. From a Maclaurin series, the summation mu raised to power x raised to power x factorial. I don't know whether you've come across that before. When you have is mu raised to power 0 is 0 factorial plus mu raised to power 1 divided by 1 factorial plus mu raised to power 2 divided by 2 factorial, and so on like that. This is more or less like 1 plus mu raised to power 2 over 2 factorial, and so on like that. Mathematically speaking, if we want to rewrite that, we're basically going to say it's equal to exponential raised to power mu. Okay, now what are we talking about? If you take a look at this guy now, we call that exponential raised to power mu. By the time you combine with this guy now, automatically that is going to give you 1. So take a look at that. So that is how we can actually prove that the sum of that probability mass function, which is a Poisson distribution, is basically going to give us 1. So take a look at that. Okay, so the next thing I want to talk about now, when we have a probability distribution in place, of course, what we basically want to do is we got some property of a probability distribution, just like what we did in a discrete uniform, just like what we did in Bernoulli and binomial and geometric distribution. We find a way to find the mean and variance. Of course, we can also derive the mean and variance of a Poisson distribution. And some of you may be wondering, why are we interested in that if X is a random variable? And of course, we basically want to figure out what the average is basically going to be. Okay, the expected value of X now is what we mean by average. And of course, if we know the average of that, how are we actually going to tell? Okay, how can we actually rely on the average? And that is the reason why we also need the variance. But you know what I want to show you now? I basically want to show, what you have here now is how to show that the expected value of X, if X actually follow a no, Poisson distribution, of course, the expected value of X is going to be equal to mu. And you know what? You remember what we did before? The expected value of X for discrete random variable is basically going to be summation X f of S. I think you remember that. And of course, the f of S right now is this guy here, which is taken from the Poisson distribution. Okay, so when I plug in that now, okay, now I'm actually going to find myself in this situation now. And when I find myself in that situation now, there's something that we want to do now. Okay, if I introduce mu and mu raised to power minus one, of course, they're going to cancel out. But the mu here, I'm actually going to ask it to come to the back of the summation, and the mu minus one. I'm basically going to combine with that, and that will automatically give me this guy now. And I got a mu here. Take a look at that. And you know what? If you take a look at the S factorial, you remember the other time I said S factorial is actually equal to X into X minus one factorial. And you know what? When I put that, the X here is basically going to cancel X there, and the only thing you're going to have left is going to be X minus one factorial. Now take a look at that now. Now this is where we are now. Okay, is there anyone who really want to ask question, or who doesn't actually understand this? Is there anyone who need clarification on how I get to that? Is there anyone? Okay, now where we are now, so we're basically gonna let that guy, we're gonna say let y, okay, represent x minus one, okay, and don't forget initially s start from 0, 1, 2 up to infinity. And of course, if I'm starting if y equal to x minus 1 now, okay, so what I'm gonna have, okay, if you take a look at where we are now, the moment we have x minus 1, we are not going to have s start from 0 anymore. We're basically going to have s start from 1, and only condition for us to go back, to something start from 0. Of course, we are actually saying y equal to x minus 1, and by the time you plug in y now, you're basically going to start from 0. And you know what? Take a look at this guy now. Okay, take a look at that guy now. We use the idea of Maclaurin series, and of course, that guy is going to be his exponential raised to power mu. And this guy can cancel this guy now, and we're only going to have mu. So take a look at that. So that is how we derive the mean, the expectation of x. If a random variable x follow Poisson distribution, that is exactly what we actually going to have for mu. So take a look at that. Now, another thing we may want to find is, how do we want to find the variance, okay? Because when we have the expectation of x, we basically need the variance of x as well. But you know what? The variance of x is a expected value of s squared minus the expected value of x or squared. Don't forget, we've already proved that the expected value of x equal to mu. But what we're looking for now is the expected value of x squared. But you know what? We may not be able to find the expected value of x squared directly. You know what we're basically going to do? The expected value of x squared is the same thing as expected value of x into x minus 1 plus the expected value of x. Okay, so and of course, we know this guy is mu, so it means we need to first obtain the expected value of x into x minus 1, okay, before we can eventually derive the variance. Okay, and that is exactly what we're doing here. We basically want to find the expected value of x into x minus 1. Okay, and you know what, if I actually want to do that, expected value into x minus 1 is typically going to be equal to, for any discrete random variable, is basically going to be that. Okay, and you know what, the f of s is the Poisson distribution, because the Poisson distribution is the distribution under consideration. Now take a look at what we have now. Now the next thing we basically going to do now, you remember the other time when I was deriving the mean, I actually introduced mu and mu raised to power minus 1. But you know what I'm going to do now? Now, if you take a look at now, you understand how how we have that. The next thing we're gonna do now, okay, if we have x into x minus 1, take a look at this x factorial. How can we rewrite x factorial? Okay, it's the same as x into x minus 1 and x minus 2 factorial. Okay, right here now, if I put that x into x minus 1, x minus 2 factorial, automatically that guy is going to cancel that guy out, and that is how we arrive at this. But you know what, you are not going to have s starting from 0 anymore, because I mean, what you're going to do is to start from 2, because you have x minus 2. Now at this junction now, what am I going to do? Okay, you're going to see the power of mu here is x, but that is divided by x minus 2 factorial. We want a situation whereby the power of the mu is going to be what is being divided. So what I'm going to do, I'm actually going to introduce mu raised to power 2 and mu raised to power minus 2. Of course, they're basically going to cancel out, but we actually need them. You know what I'm going to do? The mu square now, I'm going to bring it outside the summation sign, but this guy, I'm actually going to combine with that, and that will automatically give me this. Okay, I believe everybody now, how we arrive at this. Oh my God, what we can do now, you're going to see now, mu, the power of the mu now, it is the same thing as what is being divided by, look at that, s minus 2 here and s minus 2 here, and we can actually plug in y. We can say y equal to x minus 2. Okay, at the time we put y, we actually arrive here. Oh my God, take a look at this now. This is a Poisson distribution, right? And of course, when you sum any probability distribution, automatically that is going to give you 1. And if you multiply mu squared by 1 now, that is basically going to be mu squared. And of course, it means the expectation of x into x minus 1 equal to mu squared. Now, the moment we get that, we can now obtain the expression for the variance. Don't forget, the variance of s is defined as that. And you know what I told you the other time, the expected value of s squared, you cannot obtain that directly. Expected value of s squared is the same thing as this guy here. And of course, all what I'm just going to do is to plug in, okay, the expected value of s into s minus 1 that I got, and the expected value of x. Of course, For this guy, we got a mu squared, and the expected value of S is mu, and the expected value of S squared is actually that guy. And this guy now cancel that guy. And what do we have? We got a mu now. So what is the implication? You're gonna see that for Poisson distribution, the mean and the variance are the same. I'm gonna say that again. For Poisson distribution, the mean, which is the expected value of S, equal to mu, and the variance of S equal to mu. Take a look at that. Is there anyone now who actually want to ask question or who need clarification? Because what I've derived now for Poisson distribution, we've been able to derive the mean and variance. Is there anyone who need clarification with that? Okay, I think I want to confirm again if everyone is hearing me clearly. If you are hearing me clearly, I need you to say yes or you comment yes. Oh my God, thank you so much. Thank you so much for hearing me clearly. Okay, now I think I basically, I've already shown you now how we can derive the property of a Poisson distribution, the mean and the variance. But you know what I want to show you now, I actually want to show you how we derive Poisson distribution in the first place. I want to tell you now the origin of Poisson distribution is actually from binomial distribution. I'm going to say that again. The origin of Poisson distribution is actually from binomial distribution. What I'm trying to say now, we can actually derive Poisson distribution from binomial distribution, but I'm going to tell you the condition under which that can happen. Of course, the condition under which that can happen, situation where the n is very, very large and the probability of getting success is very, very small. Don't forget, in binomial distribution, okay, P actually represent the probability of success. I'm going to say that again. P in binomial distribution represent the probability of success, and of course, N is the numbers of trial, and the situation where the numbers of trial is very, very large, and the probability of success is very, very small. Of course, the binomial distribution is basically going to converge to Poisson distribution. And let me tell you this, the application of Poisson distribution, we use Poisson distribution to model real event. Oh my God, real event is event that occur in a blue moon. For instance, if I want to know the number of snake bites that one can have in a year in a particular state or in a particular neighborhood, snake don't just bite. That actually occur on a blue moon. Or I just want to talk about how many accidents that occur in a particular street. Okay, those are real events. Of course, that can actually be modeled by Poisson distribution. Now, I think I've just told you now why that happened. And you know what I'm trying to show you here is just like, okay, when I have a binomial mass function defined as that, and if I take a limit as n tend to infinity, okay, if I take a limit as n tend to infinity, that will automatically going to lead us to Poisson distribution. That's exactly what we're trying to show here. Okay, don't forget the P is actually because when n tends to infinity and P tend to 0, okay, NP in binomial, don't forget, in binomial distribution, the expected value of S is NP. NP is going to tend to mu. Don't forget that very mu is the mean of the Poisson distribution. And of course, if I want to find P now, what am I going to say? So P is basically mu divided by N. And that is the reason why you see me plugging in place of P and plug in mu divided by N. Okay, take a look at that. And you know what? The N factorial here is actually going to be N to N minus 1, N minus 2, N minus 3, up to the last, this is the last part of that. And you know what? If you try to simplify what we have now, if you follow that, we're going to end up in Poisson distribution. Okay, that's going to end up. And don't forget, this is actually, a standard. Okay, because this is part of it. Take a look at that. Don't forget, I tell you, you were actually looking at the limit of the whole thing, and the limit of this guy is exponential raised to power minus mu. That's a standard. Okay, you can revisit that. Okay, um, if you take a look at that guy now, okay, at the end of the day, we basically going to, if you follow that, we're basically gonna end up, in Poisson distribution. Okay, you can actually follow that. Okay, we're gonna end up, because if you take a look at this, if this guy is actually this, okay, and if you take a look at this guy, it's gonna be 1. Okay, why is it going to be 1? Don't forget, n tends to infinity. Okay, this guy, k over n is going to be 0. Don't forget, I said p will tend to 0, and 1 minus 0 is just going to be 1. And of course, and this guy here, it is this guy at n tend to infinity. And you know what I have left now? Oh my God, what I have left now is basically mu raised to power x exponential raised to power mu divided by x factorial, which is actually the probability mass function of a Poisson distribution. And this is how to show that a Poisson distribution can actually be derived from binomial distribution when the sample size tend to infinity and p tend to 0. Take a look at that. Okay, now I think you've been able to see that now. Okay, and of course, the discussion here is just to tell you that we actually, Poisson process actually follow from a Bernoulli random variable. The other time I told you the generalization of Bernoulli is binomial, and right now, you're basically going to see that we have succeeded in proving, Poisson from a binomial distribution. Okay, now as far as so let me just talk a little bit about Poisson process now. Okay, let me see. Okay, so I just wanted to say this. If we imagine a bunch of independent and identically distributed Bernoulli random variable that represent the presence or absence of a point. Don't forget, Bernoulli is used to model, dichotomous outcome. Okay, it's it's either it is present or absence. Take a look at that. Okay, of a point in a region of the space. Okay, then we denote that ST where T lies in T, and where the elements of T are the regions. Okay, we assume the element T are disjoint set. You know what I mean by disjoint set? It means they are independent. It means there's no connection at all. I think I'm going to show you what there's a particular thing that I want to show you here. Okay, this is what I mean. If you partition this guy now, look at that. You have a region of disjoint. Okay, so, and that is the reason why we said if you really want to define Poisson process now, we're basically going to say a random pattern of points in space is called a spatial point process, and such a process is called a Poisson process if, of course, the following hold. Okay, you have a 1 up to a k, They are joint, they are disjoint region. Disjoint region means they're actually independent, and they are independent. Then for any region, okay, the random variable as a has a Poisson distribution. So what we're trying to say is that this has a Poisson distribution, that has a Poisson distribution, each of them has a Poisson distribution, and you know what? If each of them has a Poisson distribution now, that they are independent, of course, they follow Poisson process. Okay, now the next thing that I actually want to talk about now, okay, how can we actually recognize the shape of a Poisson distribution? Everybody, I know some of you are familiar with a normal distribution shape. And I want to tell you this, if you have given a data set, if you have a data set and you basically want to know the shape of a particular set of data, you're basically going to construct histogram. Okay, the histogram, we actually looking at that, you'll be able to know whether the data set is normally distributed or not. And I want to tell you now, if you have, counts in subregions that I actually showed you the other time, if you try to get a histogram of that, it's basically going to look like what you are seeing now. Okay, now I want to tell you Poisson distribution is skewed. Okay, is skewed to the right. Okay, as you can see right here, the Poisson distribution is skewed. Okay, Poisson distribution is not is a deviation from normal distribution. Okay, I just told you now, when you have some set of data, of course, you can actually, if you draw the histogram of that, you're basically going to see whether whether it is skewed to the right or skewed to the left, or is a balanced one. So take a look at what you see now. Okay, so you have two histogram right here. You have the theoretical one and you have the empirical one. And you know what, you may want to ask, what is the difference between the two? Okay, the theoretical one, before you actually go, before you collect your data set, that is what we expect. That is a kind of shape that we actually expect for, Poisson distribution. And you know what? For the empirical one, that is the one you actually obtain when analyze your data set, by actually, constructing the histogram from that. So take a look at what we have now. Okay. So if you take a look at this now, okay, so that is what I'm just trying to show you. Okay, now I think we need to go into an example now. Okay, the Poisson process is actually considered a reasonable model for any pattern of point in space where a space can be any dimension. Okay, it can be any dimension, and for one dimension now, we may want to talk about the time of course arriving at a course center. I'm going to say, okay, the times of course arriving at a course center actually follow Poisson process, but because I want to tell you, course actually arrive at random. They arrive at random. You get what I mean? Okay. And not only that, what about customers, arriving a public place? What about the times of radioactive decays? I don't know whether for those of you who have done physics before, whether you've heard about radioactivity that we actually call the spontaneous disintegration of atomic nuclei. Okay, I don't know whether you've heard about half-life. Has anybody here heard about half-life before of a radioactive material? If you have heard about that, I need you to say yes, or you comment yes. Oh my God, a good number of them have asked about that. Good job. Okay, now if you take a look at that, I think I've talked about the one-dimensional now. Okay, but if you want to talk about for two-dimensional, you can look at the pattern of antis on a plane. Okay, or you look at that of a prairie dog or trees in a forest. So take a look at that. And we have three-dimensional as well. Okay, so I'm trying to give an example now, the real life practical situation, or the example of a Poisson process. Okay, now another thing I actually want to talk about now, what is the distribution of the numbers of raisins in a box of raisin bran? Okay, and let me tell you this, in statistical analysis, and particularly in let me just say, in statistical theory generally, if you really want to uh, make an inference from data, I told you the other time, we find ourselves in a world where we basically need information to be able to understand our environment. And you know what? The information that we actually need is embedded in the data set. I'm going to say that again. The information that we actually need, that will translate into knowledge, that will enable us to understand our political environment, our medical environment, our sociological environment, and so on like that. That knowledge, that information is embedded in data set. And you know what? When we have data set and we really want to have access to the information, the data set need to be analyzed. And part of the procedure to do that is actually to understand what is the probability distribution of that particular set of data, because we need to know that, and so that we'll be able to know how to approach that. Okay, the knowledge of probability distribution of the data set is very, very important. Okay, so we have a kind of technique in statistics that we can actually use to figure out the probability distribution of a random variable, because we basically want to know whether it's a Poisson distribution, or is it a geometric distribution, or is it discrete uniform, and so on like that. Okay, now if it is Poisson distribution, I just ask a question now: what is the distribution of the numbers of raisins in a box of raisin bran? And of course, if we actually conclude that that can be adequately described by Poisson distribution, then we can actually use the parameter in the Poisson distribution, to actually to take decision regarding that. Don't forget, the parameter in Poisson distribution is actually the mean. Okay, which means if I want to know the average numbers of raising now, I'm actually going to use the mean of Poisson distribution. Okay, now another thing that I want to talk about now, you remember if x1 up to xn, okay, follow geometric distribution. Okay, we've already done, we did geometric distribution on Monday, okay, where I told you the geometric distribution is actually the probability distribution that we use to model in a situation where we want to consider the number of failures before we record a false success. And you know what? If x1 up to xn follow IID geometric distribution random variable, and we decided to add that together now, and we have y. What is the distribution of y? We know the distribution of each component x1 up to xn, each follow geometric distribution, and we basically want to determine why. Let me tell you this: where are we actually going now? Where we are going now, we basically want to have a way to generalize geometric distribution. Let me tell you now, do you know when we have a Bernoulli random variable and when they are IID, when we add them together, when you add Bernoulli random variable together, that actually gives us binomial. And because of that, we're going to say binomial is a generalization of Bernoulli. But right now, each of these variables is geometric distribution. When we add them together, automatically it's going to give us another new distribution that I'm going to talk about today, which we call negative binomial. Okay, when we had, I'm going to say that again. I'm going to say that again. When each variable is geometric and I add them up, okay, if I add them up, of course, the new variable now is going to follow another new distribution that we call negative binomial. Okay, but let me tell you this, the negative binomial, this is the probability mass function for negative binomial now. And some of you may be wondering, what is the difference between the negative binomial and the geometric distribution in terms of application? I'm going to tell you now, the geometric distribution, is actually used when we're trying to, we want to know the number of failures that we actually, before we can record the first success. But as for negative binomial distribution, okay, that one is trying to say, okay, how many failures am I going to have before I started recording a good number of successes? Oh my God, oh my God, the geometric distribution is talking about the first success, but why negative binomial is talking about a good number of successes, not just the first success. We're talking about a good number of successes. I'm going to give you an example now. Okay. If, right now, I think there was January 6th, a public hearing that is going on in the United States. Okay. And I think one actually, they showed one yesterday, and maybe I did not watch that, and I'm trying to ask my student, oh, did you watch the hearing yesterday? If I go from student number one and the number one said, no, I didn't watch that. Number two student said, no, no, no. And I get here now, somebody said, yes, yes. Oh my God, you take a look at that. We are having a good number of yeses now after a series of no's. Okay, this is basically going to follow negative binomial distribution. So take a look at that. Okay, writing that in a short form now, that is it. Okay, N comma P, that's a negative binomial distribution, and this is a mathematical architecture for that. Okay, so I think I just demonstrated now that the sum of random variable, and where each of that follow geometric distribution, we actually end up in negative binomial distribution. I just wanted to take note of that. Okay, now do you know when you have a negative binomial distribution, just like every other probability distribution, we can also derive the mean and variance. But let me tell you now, if you know the mean and variance of geometric distribution, do you know that we can actually use the law of linearity? We can use the law of linearity of expectation. Okay, we can use the law of linearity of expectation to figure out the mean and variance of a negative binomial distribution, because we know that the random, if x1 follow Bernoulli, if x1 follow Bernoulli and s2 follow Bernoulli up to Sn, okay, and you know the sum of this is basically going to follow binomial. And you know, if I'm talking about Bernoulli, the expected value of x is basically going to be equal to p. And of course, if I want to talk about binomial now, which is the sum of the Bernoulli, of course, what do you think I'm actually going to do? If each of these is identically and independently distributed, they're basically going to have the same mean, which is going to be p, 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 right? When I have p, p, p in n time, it's going to be np. Okay, take a look at that. So which means I can do the same, you know, for negative binomial distribution. If I know the mean of a geometric distribution, all what I just need to do is to generalize that. Oh my God, you're gonna see now. Okay, you know, the other time when you have, you know, for geometric distribution, I think I derive, you know, when a random variable x, okay, follow geometric distribution, the expected value of x, the expected value of x is 1 minus p over p. The variance of x is 1 minus p over p squared. You already know that from geometric distribution. If I want to generalize that, if I want to get the negative binomial distribution, and since I know that negative binomial distribution is a generalization of a geometric distribution, or what I'm just going to do, and don't forget, you know, for negative binomial distribution, I need to add up, I need to add each of, you know, I need to add each of the, you know, geometrical distribution. And you know, when you take the expectation of that, don't forget, using the law of linearity of expectation, of course, I'm actually going to have that, oh my God, up to Sn. And since each of them have the same, you know, for geometric distribution, it is that. Okay, when you do that to n, you just multiply that by n. Okay, and the same thing applicable to variance. Okay, and of course, I want to ask this question now. Okay, I want to ask this question now. Okay, take a look at this. Okay, can somebody tell me what assumption do you think I actually, you know, consider here for me to be able to write variance like that? Why is it that the covariance is not showing up? Can somebody tell me now? Why is it that the covariance, you know what I mean, covariance, why is it that it is not showing up in the formula here? Can somebody tell me for extra credit? Okay, somebody share with me now. Let me look at that. Oh, somebody say independent. Good job. Send a message to me for extra credit. It's because we are zooming that x1 up to xn are independent, and that is the reason. Okay, now you've already seen the mean and variance of negative binomial distribution. We actually use the idea of geometric, okay, and with the law of linearity of expectation, we're able to arrive at that. Okay, the last thing for today, I want to talk about convolution. Okay, today, the last day today, I'm going to talk about convolution. And you know what? I'm actually going to spend additional 5 minutes to finish this up. Okay, now when we're talking about convolution now, okay, if, you know, if we actually have x and y, okay, I want to start, you know, for just two variables, if x and y are independent random variable, and each of them has a probability distribution. Okay, x and y are discrete now. Okay, x follow a particular probability distribution of a discrete type, and y also follow a particular probability distribution of a discrete type. But you know what? You know what I'm thinking? If I had x to y, okay, and I want to obtain the PMF of the resulting, you know, variable, which is z, I can use the idea of convolution to do that. Okay, but you know what? Don't forget, from independent, if x, since we said x and y are independent, of course, you know the probability of the joint of x and y we basically going to be equal to the product of the marginals. I think you already know that. Okay, now the next thing that we actually want to do now, okay, by independence now, we can actually, we want to map from XY to SZ, okay? We can also do from XY to YZ, okay? But in convolution, if I decide to go by this, I can also do the same, like, okay, you know what? I basically want to have y of z, but if I want to have y of z, is basically going to be f of y and probably, uh, that, okay, if I really want to, but right now I'm choosing to do that in terms of x, okay, since you know that z equal to x plus y automatically, and don't forget, we have the f of x, we have the g of y, and of course, if I want to find x here, okay, x is basically going to be z minus y, okay, and if I want to find, y is going to be z minus x. So you know what I'm going to do now, okay, since this is g of y, I'm actually going to plug in that there, look at that now, so that I can say, that's equal to that, okay. Now, in order for that to make sense, we have to define that g of y, okay, equal to 0, okay, for values of y not in the support of y. I just wanted to take note of that. Okay, so we are using the idea of convolution now, okay, for situation where we have a probability function for x and function for y, and we basically want to define the probability of the sum of that using a convolution approach. Okay, so you know, the probability of z now, which is a new variable, of course, it means I'm actually, since I have that, since I now have x and z, and I'm looking for the probability of z, then it means, the convolution network, I'm actually going to sum that with respect to x. Okay, I only have a function of x and z, and the interest is on probability of z. Now, what I'm going to do, I'm actually going to sum that with respect to the variable I'm not interested in. Okay, so take a look at that. Okay, so if you now see now, what I'm trying to say now, if you now want to apply this, probably to Poisson distribution, okay, maybe we want to assume now, if x and y, they are independent Poisson, s follow Poisson, y follow Poisson, and of course, we actually want to get the probability, if I now had x to y, if x follow Poisson distribution and y follow Poisson distribution, what is the probability distribution of the sum of them when I had s to y? What would be the probability distribution? Of course, we're actually using the convolution approach now. Okay, the f of x, okay, is Poisson. Okay, I'm gonna have that exponential. Okay, raised to power minus mu raised to power x over x factorial. And when you take a look at here now, okay, you for the one for the y, where we have f of y probably equal to exponential raised to power v. Okay, the mu, the two of them, they don't have the same mu. I wanted to take note of that. So this divided by y factorial, this is a Poisson for y, this is a Poisson for x. For x, the mu is actually mu, and for for y, the mu is actually v. And of course, using the convolution now, you're basically going to see, what do you have here before we have g of y, right? Then it means you're basically going to substitute, the z minus x. So that is why you have that. Okay, that's how we have all this now. If I basically now want to find the h of z, I'm actually going to sum that over the range of the variable that I'm not interested in. Okay, so if you follow that, okay, if you follow that, you're basically going to have, this is going to be the end result. Okay, if you take a look at what you have done using the convolution now, okay, you can actually, you know, the mu plus v raised to power z divided by the z factorial. And of course, when you take a look at what we have here now, if you follow what we have, you're basically going to end up, okay, here. I think somebody chat with me now. Let me just check what the person said. He said, why do we do z minus x for the parameter in G, but not in F? Oh my God, that's a very good question. Do you know that I'm doing that for X? I can decide to do that for Y. You're going to get the same. I'm going to say that again. Okay, take a look at this. Instead of you can actually try that. For those of you who try that, okay, I want you to send it to me. You can have an extra credit. You know, instead of me to do this, I can just write h of z, okay, equals summation, then y. I'm actually going to be using y, okay? And if I'm using y now, okay, this is basically going to be z minus y, then I'm basically going to have g of y, okay? What I'm trying to tell you now, if you go by this, okay, it's going to give you the same result that guy is going to give, okay? I want you to try that. Okay, you're only going to be summing with respect to y, and the other one you sum it with respect to x. And if somebody try that, oh my God, if you try that, instead of you to use the one for z or for instead of you to follow the one here, if you actually use the one for y, you if you get the same result, you can actually share that with me. Oh my God, what is very interesting here now, what is interesting here is that this is also a Poisson distribution, okay? A Poisson distribution, only that the parameter has changed now. The parameter is now the addition of the parameter of the respective distribution. So which means if it is mathematically proved and statistically observed, if x follow Poisson distribution and y follow Poisson distribution, the addition of that will also give us Poisson distribution, only that the parameter of the individual Poisson distribution will be added together. And that's exactly what you see now. Okay, that is the resulting distribution. Okay, so that is the resulting distribution. Okay, now if x1 up to xn are independent but not necessarily identical distributed random variable, si having the Poisson distribution, then y equal to x1 up to xn also have the Poisson distribution with the addition. You know what I'm trying to do here now? I'm trying to generalize that. Okay, you know, initially I actually look at the x follow Poisson, y follow Poisson, added them together. We also follow Poisson, only that the parameter is going to be the addition of the two mu. But right now, if you generalize, okay, like this, of course, the new distribution you're basically going to have is going to be that. Oh my God. Oh my God. That is going to be the end of my lecture today. I'm sorry that I have to use additional 5 minutes. Thank you for granting me that. Is there anyone who need clarification before I go today? Okay, so well, I want to thank everyone for attending my lecture today. Oh my God, thank you too. Thank you too. I'm back. Like I said, I'm back now. Okay. Today wash out. You are like you want to see your midterm one. Okay. Sorry about that. I think the TA actually promised that that is going to be available on Thursday. Sorry about that. So you're gonna see your result tomorrow. Okay, so I want to thank everyone who have attended my lecture today. I hope you're enjoying it. Until tomorrow that I'm actually going to come your way again. Make sure you stay safe. I have a lovely day. Bye for now, everyone.